Hello everyone. In today's video we're going to take a look at section 7.5, which is about expressions that contain several radical terms. Let's begin by considering an example. Suppose we want to add together 3 plus root 7 plus 2 plus root 7. If we want to add these two expressions together, we can focus on the coefficients of root 7, 3 and 2. We can just add together 3 and 2, we get 5 root 7. You can almost treat the root 7 as if it's a variable, like x or something, and then it's like 3x plus 2x is 5x, if that helps in some way. Let's consider another expression. Let's say we've got 6 times the cube root. Or sorry, actually I want to take a look at a different kind of example. Let's suppose that we have something like 3 times the square root of 8 minus 5 times the square root of 2. So notice in example 1 we had like radicals, root 7, root 7. Here we've got different radicals, but the goal will be to write them as like radicals. So this is what I mean. 3 times the square root of 8 is the same thing as 3 times the square root of, actually perhaps I'll write it like this. This is the same thing as 3 times the square root of 4 times 2 minus 5 to the square root of 2. So I've just written 8 is 4 times 2. And now what's going to happen here is the square root of 4 will come out, so we get 3 root 4 times root 2 minus 5 times root 2. Now we can simplify root 4. We know that's just 2, so really we've got 3 times 2, that's 6 root 2. And we're subtracting 5 root 2. And at the end of the day, this just leaves us with root 2. Because you've got 6 minus 5, so we really just got like a coefficient of 1. So there's a couple of different examples. We've covered one where they're like radicals, one where they're not like radicals, and one that we can simplify. But let's take a look at another example. Let's look at something a little bit well, similar to what we just looked at, except with one extra complication entering the equation. So actually, let's look at example 3b. This is going to be the cube root of 2x to the 6th, y to the 4th. We're taking that cube root expression and adding 7 times the cube root of 2y. Okay, so we would like for them to be like radicals, so perhaps we should try to simplify the one that isn't fully simplified yet. So we'll use some tools that we know from before, and in particular, remember that if you have something of this form, you can always convert it into exponential form. So that's what I'll do here. I'll write this as 2x to the 6th, y to the 4th, to the 1/3 power. I'll leave this guy alone because eventually I'm going to make the radicals the same, and I'm going to make it equal to this for the radicand of this guy. So let's simplify this guy now. So we've got 2 to the 1/3 times x to the 6th to the 1/3. So we multiply. So 6 times 1/3 is 2. So we get x squared. And we get y to the 4 over 3 plus, same thing, 7 times the cube root of 2y. Okay. So now we're almost there. We just want to kind of get things back into radical form. So Notice, well, before I even do that, notice first that this y to the 4/3 is the same thing as y times y to the 1/3. Because 4/3 is just 1 plus 1/3. Rewriting that. And so now this is nice because now we can basically pull out all this stuff, the x squared y, that goes in front. And now all we've got left over is 2 to the 1/3 and y to the 1/3. Well, that's the same thing as the cube root of 2y plus 7 times the cube root of 2y. And now we've got this cube root 2y rather, sorry if I misspoke earlier, cube root of 2y term in common. So we can like perhaps factor that out. The cube root of 2y times x squared y plus 7. That's probably how I'd write it in its final form. Okay, now we're going to move on to the next section, or the next part of this section, which is going to be focused on products of two or more radical terms. So scroll on to what we've done so far. Let's pan over here, zoom back in. So let's take a look at example 4b to start. So 4b gives us the cube root of y times the cube root of y squared plus the cube root of 2. That's what we need to multiply. Attempt to simplify this somehow. So we distribute. So we would have the cube root of y times the cube root of y squared plus the cube root of y times the cube root of 2. Now we apply our product rule from 7.3. So we multiply the insides together and we get the cube root of y cubed. Multiply those radicands, and then here we multiply on the inside as well, and we get 2y, and then of course the cube root of y cubed is just y. Those the cube root and the cube cancel each other out. So that's 4b. Let's try out one more from this section of examples. Let's consider what happens if we multiply the following two things. Let's say we multiply the square root of a plus the square root of b. Pan over a little more. Times the square root of a minus the square root of b. So there's a couple ways to approach this. If you have a keen mind, you might think of the difference of squares formula here, but let's suppose that you have no knowledge of difference of squares formulas, you just want to compute this. So you take the square root of a times the square root of a. That's just going to give you a. Square roots cancel in effect, right? Then you're going to get minus root ab from that multiplication here, and then plus root ab minus the square root, or sorry, minus b. Notice those two cancel out, and you're just left with a minus b. Okay, so now we're moving on to another part of the section which has to do with rationalizing denominators or numerators with two terms. So let's consider some examples. So before we only considered how to rationalize expressions that had one term, but here we're going to rationalize ones that have two terms. So where should I put this? Maybe I'll put this at the bottom now. So let's do example 5a. 5a gives us the following. We're given 4 over 7 plus root 3. And what we need to do is we need to simplify this. We need to, or rather we need to rationalize the denominator. We're going to make that denominator rational. Notice currently we've got that root 3, so it's not really rational. Hence the naming for rationalizing. We want to make it. We ultimately want to make it rational. So in this situation, the way that you make it rational, let's actually go back and observe the last example we just did. Notice that we had root a plus root b times root a minus root b. There's a name for these kinds of expressions. They're called conjugates. So these are called conjugate to one another. Let me underline to be clear. Root a plus root b. This is conjugate to root a minus root b because they're entirely the same expression. The only difference between them is the sign in between. So they're called conjugates. Now, if we come down to the bottom here, the way that you, let me zoom in too, the way that you get rid of radicals, as we actually can observe up here, notice we had these things that involve radicals, and then at the end of the day we didn't. We had a minus b. That's a rational expression. So when you multiply by that conjugate, you get rid of radicals. So that's the idea. So you get rid of radicals in the denominator in this case. So let's be a little bit more specific with what I mean. So let's go ahead and think about what's the conjugate of 7 plus root 3. Well, you keep the numbers the same, but you just change the sign in the middle. So it's 7 minus root 3. Okay, now here's what I'll do. I'll write this unsimplified in the top. And now let's observe what happens, like in exactly what happened in our last case. Those middle terms canceled out, right? So all we really had to calculate was the first and the last step of the FOIL. If you know the acronym FOIL, first, outer, inner, last. So we take 7 times 7, that's 49. And we take root 3 times minus root 3, that's minus 3. So in the denominator, we'll really just have 49 minus 3, that's 46. In the top, we could distribute if you want. Why not? We get 28 minus 4 root 3. So now we have rationalized the denominator. We no longer have radicals in the bottom. We do have radicals in the top now, but that's the trade-off. Now, there's a couple more examples where you're rationalizing the denominator, the numerator, but I want to move on to another type of example, and this has to do with terms that have differing indices. So let's pan down here. Let's take a look at terms that have different indices. So let's take a look at example 7. They want us to divide and simplify the 4th root of x plus y cubed divided by the square root of x plus y. We'll approach this by converting it into exponential notation. So remember what that means. That means in the top we'll have x plus y to the 3 over 4. And in the bottom we'll have x plus y to the, well, it's a square root, so it's 1 over 2. Now we can apply the exponent properties from way back in section 1.6. This is the same thing as subtracting our exponents and keeping the base the same. We just got x plus y to the 3/4 minus 1/2. So 3/4 minus 1/2, that's just 1/4. So we really have x plus y to the 1/4. Or in other words, if we want to bring it back to radical notation like the problem started, which is generally what you should do, you get the 4th root of x plus y. All right. So why don't we take a look at one more example. This is example 10 in the text. This will be the last one. If the divide and simplify, the cube root, let me pan down a little further. The cube roots of a squared b to the 4th divided by the square root of a b. Like in the last problem, let's go ahead and let's get it from radical form to exponential form. So radical form to exponential form, we would have a squared b to the 4th raised to the 1/3 power over ab raised to the 1/2 power. We'll apply the properties of exponents to give us a to the 2/3 times b to the 4/3 over a to the 1/2 b to the 1/2. Now we've got a to the 2/3 minus 1/2. It's the quotient rule for exponents, and times by b to the 4/3 minus 1/2. Okay, so now we just finish this up. Just with a little bit of fraction math, 2/3 minus 1/2 turns out to be 1/6. So we get a to the 1/6 times b to the, and then 4/3 minus 1/2. Well, let's think about that. That's what's 1/2 and a third. So we could say we could multiply both sides by, let's just do this off to the side. I won't do this in my head. Got 1 1/3 minus 1/2, or 4/3 minus 1/2, which is the same thing as 8/6 minus 3/6, which is just 5/6. So we've got this to the 5/6 power, and now we can just write this back in radical form. So this is like the sixth root of a b to the 5th. Okay, so that's the end of this video. We've covered a variety of topics, but ultimately everything had to do with expressions that contain several radical terms. So this is everything we did today. I hope that this video is helpful, and I'll see you all in the next video on section 7.6, where we solve radical equations. Take care.